Okay, great. I'm going to get started. So last time we talked about persistent currents of a macroscopically occupied quantum state in an annulus geometry, and we saw the idea that there can be persistent currents in such a state. So what we're going to do today is we're now going to not talk about the annular geometry. We're going to talk about just a regular fluid. And we're going to see that you get a phenomenon known as quantum vortices. And we'll spend maybe half a lecture talking about those. Then I want to shift gears. I want to talk about another phenomenon that is a property of many-body interacting systems with emergent behavior, something that we haven't talked about so far, and that is the idea of quasiparticles. It's an incredibly important idea, and when it applies, it means that you can make predictions that would otherwise be completely impossible. On the other hand, how quasiparticles actually arise is very difficult to see, and we're going to talk about a very specific example where one can literally calculate this and see that it's not nonsense. In the case of weakly interacting bosons and Bose-Einstein condensates. So this is going to be the most technically demanding part of this course. I'm going to do a calculation. I won't get it done today. It will be impossible for you to follow it in real time. The only thing that you will be able to follow in real time is the logic of it. You will not be able to follow the algebra, but if you want to check it, you should. And if you want to try your own understanding of it, I can give you a homework sheet, which I'm not going to make an official homework sheet, which is to use the same technique to look at an even harder problem, which is the problem of many-body theory for interacting electrons in a superconductor. So, but this method is fantastically powerful and has applications beyond quantum condensed matter. Okay, next thing I want to mention is we're talking about condensates, and I want to make sure that if you have not seen Bose-Einstein condensation in an elementary class in statistical mechanics or the graduate class, or you've seen it but you only vaguely remember it, or you saw it and did it, but it wasn't explained to you very well, which is usually the case, then my notes from my undergraduate and graduate course on statistical mechanics, I put them into my printed notes on emergent states matter 2.3.4, and so you should look at those. There's actually, I realize there's another thing that some of you will find useful. All of this requires using the grand canonical distribution and the idea of chemical potential. My experience is that most students do not understand why the grand canonical potential is a good thing, and why what chemical potential actually means. Okay, how many people here think that that description applies to them? Okay, for you, yes, okay.
I think I understand it, but I probably don't, based on your skepticism.
Right. So there's a way of thinking about grand canonical distribution and chemical potential, which I've never seen in any other book apart from my own books or my own notes or books, if you like. So, but I didn't put them into my ESM notes. I will put them. I will post on Teams from my StatMech notes, and so you can see. Well, once you see the idea, well, most students hate the grand canonical distribution because you have to say, well, what is this chemical potential and stuff like this? Okay, and so most students who have not been taught properly do not understand it at all. They just do it and kind of, just sort of whatever. But once you see what problem it solves, it's fantastic. You will then see, oh, this is really, really good. Okay, so now let's get going. So we're going to start with 2.4.5 in the notes. So let me go to those. And so what we're going to talk about next, I'll just use the number that I use here, quantum vortices. So our goal is to expose the existence of topological excitations even in simply connected geometries. So what we did last time was we took an annulus, and an annulus is not a simply connected, does not have a simply connected topology. Okay, it has a hole in it. Okay, but if I make a bucket, it doesn't have a hole in it. Well, hopefully it doesn't. Okay, so if it doesn't have a hole in it, then why do we care about what I just showed you last time? And so what we're going to see is that even if you don't have a hole, you can have these topological excitations, and they have a very important physical significance. So let's get going. So the basic idea is the following. So the phase of this macroscopic wave function is only defined up to modulo 2 pi. Okay, so I can add and subtract multiples of 2 phase, multiples of 2 pi. So let's suppose that I have some 3D volume of, say, a superfluid, and now I make some contour in that volume. Then what I can do is I can measure the circulation. So the integral around this contour is the superfluid velocity of the line integral of the superfluid velocity is from the formula that I wrote down before last time. The velocity is given by h bar over m times the gradient of the phase of the wave function. So this is grad gamma dotted with dr. And then this is h bar over m times the change in the phase as I go around that contour. Okay, now let's have a look at whether this integral has to be 0. So what we know is that the macroscopic wave function phi of r is single valued. So let's suppose that I have a start to this contour, and then I go all the way around, and then I get to the end. So the end is meant to be right next to the start. So what that means is that the phi start is equal to phi end. So that's what we can infer from that. But this does not imply that gamma start equals gamma end. Okay, so that's the main point. So in fact, what it does imply is that gamma at the start is equal to gamma at the end plus 2 pi n, where n is equal to 0, plus or minus 1, plus or minus 2, etc., etc. So that's what you can conclude from single valuedness. And so because of that, that's how we can conclude then that the integral of the velocity, superfluid velocity, over this contour is then going to be h bar over m times 2 pi n. And this this quantity has a name. So we call, in fluid mechanics, we call circulation VDR. And so what we've discovered is that circulation is quantized. in a macroscopically occupied quantum state. Okay, so that's the first thing, and so this is true even you know, this can be true for any path, but it's not complete. It has to be. We have to have some stipulations about this path. So now we have to look at the conditions that need to be satisfied. So what are the conditions that we need for n to be non-zero? So what we saw last time is that there is one way to do it. So one way to do it is that the region of fluid is not simply connected. So that was the annulus example, which is somewhat artificial. So that's the first thing. But there's another thing that can happen, which is there could be a region in the fluid where the superfluid density goes to 0. Well, let me just say superfluid density vanishes.
To be clear, gamma is the phase.
Yes.
While phi is the full wave function.
Yes. Yep. So those are the criteria. So let's just see what that means. So let's suppose I have a simply connected region. So if I have a simply connected region, then I can use Stokes' theorem. So what does Stokes' theorem say? So here is my region. Here is my contour. Like that. And then Stokes' theorem says that what I do is I can construct a spanning surface on top of this contour. So this is a surface on which begins on this contour. So we'll call this surface S. And then the integral, the line integral of V dot dr around the curve is equal to the integral around the surface of curl V dotted with ds, where ds is some little unit, is a vector normal to the spanning surface at this point r, and with magnitude proportional to the element of the surface area ds. So that's what Stokes' theorem is, and so then you can say, well, if we know that v is equal to h bar over m, then grad gamma, then that implies that curl of Vs is equal to 0, and so that implies that the circulation has to be 0. So that's a theorem. So the only way out of that, there is a way out of that. There is something else that can happen. So what can happen is if there is a region where for some reason rho s is equal to 0, and the contour C goes round that region, then Stokes' theorem doesn't apply. So what we have then is the situation where we have now our system. And there is our box. Here is our contour C, and somewhere in the middle of that there is a region. We draw it like this, where rho s is equal to 0, and then in that particular case, then it is possible, in this particular case, then it is possible to have a non-zero circulation. So in some sense, the system has turned itself into an annulus. The difference between this situation and the situation that we talked about last time was last time we had an annulus, so we just punched a hole in the system. We just made it into a donut, okay? Here, we're going to see, can the system self-organize to form these things spontaneously? Can this be emergent? So when we put in the annulus case, annulus, we put in the non-simply connected, in the non-simply connected nature by hand. But here, what we're doing is we're asking, can such a situation emerge spontaneously? So this is an emergent phenomenon, not one that we've put in by hand. So Frank, you're looking puzzled. Is there something you want to ask me?
I was wondering, it depends, I'm wondering about the, how fine grain can we look, because on any arbitrarily small scale, the density will go to 0.
That's true.
So
that's true. So if I'm talking about a velocity,
why would then density go to 0 if you were arbitrarily small? Shouldn't density?
Well, the space between atoms, the density is 0, right? That's what you.
That's what I mean. But if this is a boson, I understand why.
Well, even if it's a boson, your statement is a true statement. So when we talk about density, we're always talking about coarse grain. So we're always talking that we've got a coarse grained field here, which is continuous. So I've got so I'm looking at on a scale larger or of order the spacing between the particles, and I'm looking at a velocity field. Remember, if I took a snapshot, the particles are distributed like dropping pepper on a piece of paper, but they're always moving around. So at any given point in the fluid, in the space, I can look at the average density of particles there. So what we're thinking about is statistically on average, is there a high density of particles? And if there is, then I can coarse grain that and say, now I've got some coarse grained picture of the density of the system as I move from point to point in space. Similarly, if I have a coarse grained picture, so I don't see the individual atoms, then I can talk about the velocity as being something that is coarse grained. So on the scale of what happens in between point particles, which are atoms, then you could say the density is fluctuating from 1 to 0 to 1 to 0 to 1 to 0, something like that. We want to make this a function that is smooth, so we're going to coarse grain, so that this thing is turned into a smoothly varying function.
Okay, but is there is it relatively arbitrarily defined how smooth we have to get?
It is. So and you also have to stipulate that once I've done the coarse graining, any results that I obtain should not depend sensitively on whether my coarse graining scale is, say, 5 angstroms or 7 angstroms or 10 angstroms or something like that. Okay? So when you define fluid mechanics or any continuum theory of matter, you're always having to do some sort of coarse graining like that. So you have functions that I can sketch on a page that look like functions and not discontinuous wiggles like that. Okay, one more quick question and then I want to move on.
Well, my understanding is that this is a wave function. So each of these atoms aren't point particles, but each one is an extended object, and they all happen to be in the same wave function. So I guess I would have thought that we don't actually have to coarse grain because we already have a physically smooth continuous thing.
Well, I don't know if that's true.
I see.
Not even up to delta X, delta B,
Well, up to that, I mean,
H bar, I guess.
let's not go into the foundations of
Yeah,
quantum
yeah,
mechanics
of course.
because that's a rabbit hole I don't want to go down.
Okay.
It's not that just remember that I can have a smooth wave function, but that just tells me about the probability of observing a particle. It doesn't tell me if I took a snapshot of the system what the density looks like.
I see.
Right? I can, remember if I'm doing quantum Monte Carlo, I'm going to literally simulate the Schrödinger equation for 10 to the 23 particles. I will have trajectories in space-time that look like some big spaghetti. And from those, I then extract all the observables, including the density. There's nothing to stop me having density fields that are not functions from the output of that.
So,
Even though the whole thing is described by a wave function of 10 to the 23 particles.
so macroscopic quantum occupation doesn't imply that
It doesn't
the
imply
system
coarse
itself
graining.
is
No.
just a big wave function.
It does imply the system has a big wave function, but it doesn't imply that that wave function it corresponds to particles that are smoothly distributed. The particles, if I want to know where is a particle, I can do a scattering experiment. I can say, hey, the particle is there and it's not there.
Right.
Okay. All right. So very subtle, right? Glad it makes you think. Okay. So, all right. So how can such a situation emerge spontaneously? So I'm going to now tell you the answer to this. So the historical reason for this is this Onzaga and also Feynman realized an emergent wave for this to happen. And it comes from an experiment, which is Osborn's rotating bucket experiment. How do you spell Osborn? Osborn's rotating bucket. Okay, so let's have this experiment and let's see that there's a paradox here. Okay, so we're going to take a Bose-Einstein condensate. We're going to use as our Bose-Einstein condensate, we're going to use helium-2. Helium-4 isotope is a boson. And this is at a temperature lower than the temperature called the lambda transition. And at the lambda transition, about 2.17 degrees Kelvin, the super helium becomes a superfluid. And if you want to see what a superfluid does, go and watch the video on the Emergent State of Matter webpage or the Emergence in Order webpage. It's on the canvas. Go to that, watch the video. It takes about 20 minutes to see the video. It's amazing. Okay, so that's going to be our system that we're talking about, and the idea is that for temperatures, so naught is less than T lambda, which is about 2 degrees Kelvin, something like that. So above that temperature, we can think of helium-2 as being 2 interpenetrating fluids. Okay, why there's two interpenetrating fluids. So the idea is that one of those fluids is a superfluid. And that has a velocity, which is the same as the velocity, the superfluid velocity that we've been talking about. The other is called the normal component. And the reason that there's two of them is that the normal component is made up of excitations above the ground state. So if you're doing quantum mechanics, temperature is set equal to 0. Okay, it's boring. Okay, 0 temperature, you have a ground state. Now we're at a temperature, let's say 1.6 degrees Kelvin. There's a ground state, which might be a Bose-Einstein condensate. There's a macroscopic wave function, but there are also some particles in the system that are excited by thermal fluctuations, and they will not be part of the macroscopic occupation because they've been excited away. So those thermal excitations above the ground state cannot be Bose-Einstein condensed. They cannot be part of the macroscopic wave function of the system. So what that means is that there is a Vs, which is the superfluid component. And there's a Vn, which is the normal component. So if you want to do hydrodynamics of helium below 2.2, whatever it is, degrees Kelvin, you have to now do quantum hydrodynamics. You have to do the hydrodynamics of the condensate coupled to the hydrodynamics of the normal component. And how you couple them together is extremely complicated, and I would say is not fully understood even today. Okay, so but we don't need to understand it fully in order to be able to proceed. Okay, so basically, I want you to think of the normal fluid as just being a velocity field in space, which obeys all the normal fluid equations, has viscosity, it looks just like Navier-Stokes fluid. And then you have the superfluid component, which is curl free. Its curl V is equal to 0 because it came from the phase of a macroscopic quantum wave function. So that's a picture, and that picture is called the two fluid model. Okay, so that's the picture. So now let us ask what happens when you rotate helium-2 in a bucket. What happens? So let's try to figure it out. So here's my picture. So here is my bucket. I'm going to rotate it about the central axis with some rotation vector omega like that. So it's going around like this. And what would we expect to see if we had a regular fluid? So just take your coffee, put it in a bucket and rotate it. What's going to happen? It's going to do that. You're going to form a meniscus. What shape is the meniscus going to be? Parabola. Very good. So we can say that this is the height, Z, as a function of, say, the radius from the center. And so if we know it is going as omega, we would say that Z as a function of R is going to be omega squared R squared, and then of course there's gravity pointing down. So it's going to be omega squared R squared over 2G. And you can calculate that just by working out what is the chemical potential. And you've seen this before, right?
Yeah, I saw this in a mechanics class.
Great. Okay, great. So what would we expect in helium? So in helium-2, So what do we know? According to the two-fluid model, what we would say in the two-fluid model is that the total density of fluid is equal to the density of the superfluid plus the density of the normal fluid. So we'd say something like that, okay? And then we would say, well, that's true. And also, please remember that this is a function of temperature, and this is a function of temperature, because from above the lambda point, there is no superfluid, so everything is just this. If I'm below it, if I'm 1 millikelvin below the lambda point, I've got a tiny bit of superfluid component, but then it's relatively hot, so then there's lots of excitations above the ground state, and so this will be large and this will be small. And this thing grows from 0 as you go below the lambda point. So this, if I were to draw this as a function of temperature, so there is T lambda, here is rho S, and so what you might imagine naively is that this thing is going to be 0 over here, and then this is going to grow in some way like this towards 1. So that's what you would expect. And this thing, rho n, if I were to draw rho n on the same graph, rho n will go to 0, you would think, at 0 temperature, and would go up to being, say, 1 at T lambda. So that's what you would expect, and it's pretty much true, particularly for non-interacting projects. Okay, so that's what you would expect. So let's work out what happened to the bucket. So for the bucket of helium, the superfluid part and it flows without viscosity. Okay, I'm going to show you why that's true. For now, just for now, assume that that's the truth. Okay, so remind me, I need to show you this later. Okay, so I will show you that, but I realize I haven't shown it to you for now. So let's just assume that that's true. So when I rotate the walls of the bucket, the superfluid part isn't going to rotate because it's got no viscosity. I've got no way to move it. So what will happen is the normal part will rotate, but not the superfluid part. So what I would say then is actually this means that the fraction of rotating fluid fraction of rotating helium-2 is rho n over rho. So what we would then expect is that z as a function of r is then going to be rho n of t over rho times omega squared r squared over 2g. Okay? So that's a prediction. So we can make that prediction. Now we can go to experiment and see if it's true. Okay? So this implies that the meniscus is temperature dependent. Okay, it's not true. I'm going to say it's basically not true because it depends on how fast you rotate it to some extent, and I will, if I have time, go into that. It's basically not true. The whole superfluid rotates as a rigid body. Okay. This is not quite true, okay? But this is where when they did the original experiment, it was close to being true, within their experimental error, and so we understand it better now. But this is basically what you're seeing. So let's just take this as a given, although it does need to be made more nuanced. And so we have to understand, how is this possible? So if this, given that this is the case, the question we should ask is how is this possible?
And of course, all this is in steady state.
Yes, it's a steady state. So this can't happen, and let's just see why. So we know that the velocity is equal to omega. I called it omega, I've used that symbol. So whereas here, little omega, I mean big omega, doesn't really matter. So if I have a rigid body that is rotating, then velocity is given by omega cross r. And if I have, and if omega, and if this is, and if I then work out what curl of V is, so V is omega cross r, and that says that curl of V is equal to 2 omega. And that's not possible because we know that curl of V for a superfluid component has to be 0. So this is a problem. This is a problem for a superfluid. And it's because the superfluid has the property that curl Vs is equal to 0, and that's implied by the fact that Vs is h bar over m grad gamma. So this is a paradox, and so what is happening is at these rotation rates, we form quantum vortices. So if I'm not going to show you an actual experimental picture, but if I did, it would look like this. And this has been seen in superfluid helium. It's been seen in rotating Bose-Einstein condensates. As you rotate it, what you form is an array of quantum vortices, or a lattice of quantum vortices. And the vortex is defined where the phi, the actual wave function, is equal to 0. So if I want to know where is a vortex, I look at the microscopic quantum wave function. I find the places in space where it has gone to 0. If it has gone to 0, I can't define the phase. If it has gone to 0, the magnitude is 0. If the magnitude is 0, the superfluid density is 0. So at those points in space where phi vanishes, there is no quantum fluid. And that means that if I then make a circuit around each of those locations in space, I will get a topological charge. I will get an n that is non-zero. So at those points where phi is equal to 0, that implies that the amplitude equals 0 implies rho s is equal to 0. It means the phase is undefined, and any circuit around the locus of points where R has the property that phi is equal to 0, any circuit around those points will have non-zero, or will have the ability to have n not equal to 0. So that is a quantum. That's what we mean by a quantum vortex. Okay, let's have a look at this. Phi of r is a wave function, so it is the real part plus the imaginary part. I'll call it like this. R is in three-dimensional space, and phi is a two-component order parameter. So if I want phi of r to be equal to 0, that means that phi 1 of r equals 0 and phi 2 of r equals 0. That defines the places So I've got two equations here, and R is a three-dimensional space. So what that tells you is that if R is in 3 dimensions, I've got two equations that have to be satisfied at those points in space where the vortex is. That means that the vortex must itself be a one-dimensional object, because it's not uniquely specified by two constraints. If I'm living in 2 dimensions, I've got x, I want to find x, y, and z. I want to find x, y, and z where phi of r equals 0. It must mean that I've got 3 unknowns, 2 equations, and that means that the locus of points x, y, and z is a line, or one parameter curve. If I was in 2D, I'd have 2 equations, 2 unknowns, x and y, 2 equations, and that would then give me point vortices. So when I look down at my bucket from above, that's what I have. If I look at it from the side, it looks like this. Here's my bucket. Here's my axis of rotation. I've called it omega, I've forgotten which I called it, doesn't really matter. I have my meniscus that looks like that. And then what I've told you is on the top, I can see those quantum vortex lines. So if I'm looking on the side, those quantum vortex lines are looking something like that. They're lines, not points, and they're going around like that. And what's happening is that around each vortex, the velocity field is approximately cylindrically symmetric. And so that means that if I go around one of those quantum vortex lines, then I have the integral of Vs dot dr around a contour going around one of these quantum vortex lines. So let's draw a contour in over here. So here I'm going round one of these quantum vortex lines, like so. So I've just drawn this contour over here. If I go round that contour, then that is equal to 2 pi r times Vs of r, and this r is the radius. Yeah. So let me draw this again. Here's my vortex. I'm going round the contour like this. This is the radius. So integral around that is just 2 pi r VSR. And then this is going to equal n times h over n. And so what I get is that the velocity field falls off as n h over m times 1 over 2 pi r. So the velocity field falls off with a parallel with distance from there, but so there's a circulating velocity field. So if I now draw the vortex, then what I have is a velocity field that is going around like that, and we've just calculated how its magnitude depends on distance. So now what happens when I have multiple vortices? So let's have one vortex over here, another vortex over here. Let's draw the flow pattern around the vortices. So something like this. And then let's draw the flow pattern around this other vortex. So let's use a different color. So let's draw this. Again, in the same direction. What you can see happening here in the middle here, if I just focus in on this, I've got a flow field going like that, another flow field going like that, and so they cancel out. So the flow fields from this vortex around here, the flow fields around this cancel out. And so what ends up happening is that over the whole body, the resulting flow field looks like this. So there's my bucket. I've got my vortices in the middle here in some array. It's typically a hexagonal array, something like this. And then the only parts that are going to survive, the middle parts cancel out. And so what I'm going to have left is big velocity fields in this direction, smaller ones in this direction. And so it simulates rigid body rotation. Okay, so that's the idea of what these quantum vortex lines are doing. Now I see, but I want to move on to something else. Now I want to explain to you something I didn't tell you about, which is I want to explain to you why it is that this thing has no friction. And I didn't tell you that before. I want to tell it to you, and so I need to go and find that in my notes so I can explain it to you. If I don't find it, I'll just tell you just off the top of my head. But I want to just make sure that I explain it. Just want to make sure I explain it properly. Okay, so any questions about this or clarification? Okay, very quick.
Amazing physics. I'm wondering if the velocity field falls off of one drawing, how do they cancel? I mean,
They have to organize their centers in such a way that they minimize dissipation, something like this, minimize the energy and so on. So they do it. Okay, but how, I haven't told you. Okay, all right, so let me now fill in one gap in this process. So the next thing I want to explain, I want to explain why the superfluid has no viscosity. And we needed that. We used that because we said that if it doesn't have any viscosity, then it just can't move. When I rotate the bucket, it's just going to sit there. Okay, so why superfluid has no viscosity, which implies that the rotating bucket cannot rotate the superfluid component. So in order to explain that to you, I need to tell you what viscosity is. So what question does viscosity answer? So let's so now I want to consider the following situation. Let's ask how we measure viscosity. So here is what we do: is we start off with a plate that looks like this, and we put in the middle of the plate a fluid. Okay, there's fluid inside here. And then what we do is we take this plate and move it like this, and we take this plate and move it like that. So there is a shear. So this is called a shear. Okay, so what do we expect the fluid velocity field to look like? So what we would expect is that over here, the velocity, I'm going to set up some coordinates axes. So I'm going to call this one Z, and this one X. So what we would expect is that the velocity is purely in the X direction, and then there's nothing in the Y or nothing in the Z direction. And the velocity that I have in the X direction is going to depend on the height Z. And the reason it depends on the height Z is because I've got boundary conditions. So the fluid on the boundary here is going to be moving with the boundary. That's called a no-slip boundary condition. So no-slip boundary condition at the upper and lower surfaces. So we can draw straight away what the velocity field looks like. So we know what the velocity field looks like over here, right close to the boundary. It's got to be going in that direction. Down here, right close to the boundary, it's got to be going with the same velocity as the wall. If I go further down, it's going to look like this, 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 something like that. So that's what the velocity profile is going to look like. So what's going to happen then is that there's going to be viscous drag at the wall. In other words, if this is happening, when I try to push the wall like this, I have to exert some force in order to make this happen, because the fluid is sticking to the wall, and I've created a velocity gradient in the fluid. So So there is a velocity gradient in the fluid, and that is going to exert a drag force. So to move the plates in the shear experiment, we need to apply a force. Per unit area of the plates. Okay, so the plates have got this area. I have to apply a certain force in order to move the fluid. If the fluid was, say, honey, you know, to shear honey would be very difficult. To shear a superfluid or shear a gas, very easy to do. So this is a measure of viscosity. And in fact, we define the viscosity in the following way. We say the force per unit area is proportional to the gradient of the x component of the velocity in the z direction. The steeper is this gradient, the more force I have to apply. If I just do this very gently like this, the gradient will be very small and I won't have to apply very much force. If I really want to apply a huge force, I'll create a huge gradient in the fluid. So the force that I have to apply is proportional to this gradient, and the coefficient of proportionality is called the shear viscosity. And that's the shear viscosity that comes into the Navier-Stokes equations. That's how we define it. Okay, so that's what shear viscosity is. Okay, who cares? Okay, well, we care for the following reason. Let's see what happens in the case of a superfluid. So in the case of a superfluid, we know that the velocity field is the gradient of the phase of the wave function. So curl of V is equal to 0. So let's have a look at the components of this. So this means that dvx by dz minus dvz by dx equals 0, and the same thing for the other components of the curl. Okay, well, we know that vz is equal to 0. So that means that dvx by dz must also be equal to 0. And if dvx by dz is equal to 0, that means that the force per unit area equals 0. So there is no drag force exerted by the superfluid. Now what people say is, oh, so it means a superfluid has 0 viscosity. Because they say, if F over A is equal to 0, then eta is equal to 0. Not true. Not true. Okay. All it means is that F over A is 0, but eta can still be non-zero. Okay. So F is equal to 0, even though eta for helium-2, for the superfluid, might be non-zero. Okay? This is purely because of the interplay between space and the topology of the order parameter in order parameter space. That's where this all came from. Okay, so what is the viscosity of superfluid helium? Okay, so it's about 100 to 1,000 times smaller than that of water. Okay, but it's not zero, you can measure it. Okay, so the viscosity is non-zero, but it behaves, it does not support a shear. So it effectively, people say, it behaves as if it were without viscosity. So So it behaves as if it had no viscosity. That was how people thought about it early on, okay? And today we know that that's not quite true. And that's why we couldn't rotate the bucket, why the superfluid couldn't go around with a bucket. Okay, so.
Could you have a case where vortices form in the tube, in which case you'd get a non-zero force?
In what tube?
Sorry, in this experiment, if you had vortices on the inside, then the curl of the
I could,
would be
but
non-zero.
I could, but in this experiment, I assume that the shear force is small so that the flow is long.
I see. Okay.
So then you can ask another question. Well, what happens if I take a superfluid and put my fingers into it and stir them up and make it turbulent? Okay, so we did that experiment in 1993, and you can see our paper on that in Physical Letters. And we discovered something really amazing. So what happens is that this superfluid stays a superfluid, but behaves like a classical fluid when it's turbulent. And the reason is amazing and still not fully understood. The reason is this: when you create vorticity of the normal fluid is made of excitations of the superfluid. The excitations behave like quantum particles. That's what we're getting to next. We're not going to finish it today, but we're going to get to that next. Those quasi-particles behave like particles. They're quantum particles, and they bounce off the cores of the topological defects of the vortices. And because they bounce off the cores, they exchange momentum. So the normal fluid and the superfluid components get coupled together. The topological sector of the excitations and the particle sector of the excitations get coupled. Okay. So what that means is that the normal fluid, as you put your fingers on and made the thing turbulent, that entrains the superfluid, and the superfluid then goes around with the normal fluid and does what it does. So you can still see the quantum vortices. You can still see superfluidity by looking at other excitations of the system, like second sound, which I haven't told you what that is yet. So you can use that as a tool to see the quantum aura. At the same time, you can measure the turbulence and see that the regular fluid and the superfluid got coupled together, and the whole system behaves like a classical turbulent fluid. It's amazing. Okay, it's super cool.
How do you not freeze your finger off?
You just wear gloves.
Oh.
I remember I used to work at the University of Illinois. That's the benefit of living in the Midwest. Okay, so now you know why vortices are just amazing. Yeah, it's just room temperature. We've had room temperature superconductors in Illinois for years. Okay, all right. So that's all I want to tell you about vortices and rotating condensates. There is lots more to tell you about this. I mean, I have a whole course here on just that, but I don't want to go into it. If you want me to go into it later, I can. But I want to move on to some other things, because I want to show you that some of these things that we're talking about here apply not just in weird quantum states of matter, but in non-equilibrium systems too, which are not quantum mechanical. Okay, that's the most amazing thing. Okay, so there is something else I want to tell you. What do I want to tell you? I don't need to tell you this. Okay, so there is cool stuff. I'm going to try to move on. If you want, you want me to tell you more about vortices, or do you want me to go on and start talking about quasi-particles?
I have one question about vortices.
Only one.
Only one right now. You said that they're one-dimensional, so they're like lines.
If you live in 3D, the corner vortices you create are going to be lines.
So
I didn't just say it, I proved it to you.
So can you kind of imagine them like you would imagine a vortex through like a regular fluid, or classical
A
fluid?
regular classical fluid does not have vortices.
So like if you had like a whirlpool underwater.
Does it look like a tornado? Is what you're asking? Yes.
Exactly.
The answer is yes. They do look like tornadoes, but the tornado is not quantized. Okay, so the big difference is that in the superfluid, these little tornadoes flying around are quantized. And I haven't told you this also. What happens when they cross? So they can move around, they can cross each other, and when they cross, they interact and they split each other into two and then go off in different directions.
And
You can visualize that. Friends of mine figured out how to see these quantum vortices by sticking little particles of frozen hydrogen at 1 degree Kelvin into the superfluid helium, and those particles of frozen hydrogen then stuck to the cores of the quantum vortex lines, and you can literally see them with your own eyes.
So if they're one-dimensional, then do they often close on themselves?
Yes, you're totally right.
Or do they?
No, they
go to the boundary.
You're totally right. So they have only two choices. They either begin and end on the boundaries of the system, or they form loops. If they form loops, then they have a certain energy per unit length. We can calculate that if you want me to show you how to do it. They have a certain energy per unit length. So when you take a loop and bend it like that, that costs energy. Okay. So then what's going to happen is the system is going to lower the energy by changing the radius of the loop. And so the loop will then shrink round like this and eventually poof, go away, like the smile of the Cheshire Cat. Okay. So you can see those. In the movies that my friends made, you can literally see these loops, and you see them changing like this, and you can easily work out how the radius will go as a function of time. Okay? Easy to work out. It's fantastic what you can do with quantum vortices. If you want me to give you some links to papers about it, just ask in Teams chat, okay? Okay, so more vortices or go on to quasi-particles? Quasi-particles. Okay, quasi-particles. Yeah. You want me to go back to vortices later? I can. I've left some spaces in the schedule, but we're going to go to quasi-particles. Okay, so now I'm going to tell you some new stuff. So the next thing we're going to do is we're going to look at section 3. Let's use a different color. We're going to look at section 3.1.1. And we're going to start talking about quasi-particles. Okay, so up to now, all we've talked about are the topological excitations. We've talked about the topological excitations because they're amazing. They're completely non-intuitive. They don't have classical counterparts. They exist in quantum fluids. They exist in quantum fields, such as in the early universe. In fact, the fact that you live in a galaxy, there's a very good chance that that is due to quantum vortex lines, but they're not quantum vortex lines in superfluid helium. They're quantum vortex lines in a grand unified gauge theory, and we have strong evidence. No, we have some evidence. Well, it used to be strong, then it went away, then it's come back. We have some evidence that the galaxies are seeded by quantum vortex lines, which occur in the gauge fields that describe high energy physics and very high energies in the very early stages of the universe. Okay, why? I told you that the quantum vortex line has energy per unit length. Okay, if I have a quantum vortex line in a gauge field, you can think of the gauge field as basically being like a quantum fluid, but it may have more degrees of freedom. Okay, I told you about superfluid helium has 2 component order parameter. Superfluid helium-3 has an 18 component order parameter. So if I have a grand unified theory in the early universe, it's more likely to be like superfluid helium-3. But you can still have these cosmic strings, as they're called, which are basically just quantum vortex lines in that particular order parameter. Okay, they have energy per unit length, and they're huge. They span the entire universe. Okay, so if they have energy per unit length, what else do they have?
Well, if they're the size of the universe, then they have energy.
Well, they have energy, yeah. Well, okay, it can be anything or whatever. What else do they have though? Think like a cosmologist now. Not pay attention. think like a cosmologist, not like a condensed matter physicist. Okay, I've got huge vortex lines floating around in the universe. They have energy per unit length. My question: what else do they have? Well, no, you already answered a bunch of questions. Somebody else. Somebody who hasn't answered questions today. You. Gravity. They have gravitational fields. They have a gravitational field, right? Because remember that in general relativity, if you have energy, that is the source of the gravitational field. Okay, so they have gravity. So stuff gets attracted to them. Okay, so my friends who were cosmologists, when I was postdoc 40 years ago, all my friends were people like Neil Turok, Andy Albrecht, Rob Brandenberger, and others. Okay, they were all working on inflationary universe. They were all working on cosmic strings. Why? Because when you look at the earliest galaxies, which are called Abell clusters, you see that they are not random. They have a correlation function, which in space, when you look at it and the observational data, and when you look at the correlation function, it looks just like the correlation function of a string. Okay. So that was the idea, that the Abell clusters came from cosmic strings, and the earliest galaxies were formed by cosmic strings. Okay, so after about 20 years, that idea fell out of fashion, and there were other data that showed it wasn't true, and blah, blah. I don't remember all the details of what happened. Okay, so that was fine. Now fast forward to like a year ago, maybe 18 months ago. Okay, what was the most significant discovery in astronomy? Okay, what is the instrument that made that discovery or those discoveries? The Webb telescope, right? Okay, so the Webb telescope is amazing and has done all sorts of interesting things. What is the most strange thing that it has discovered? Exactly. It has discovered, when you look back in time, you see that there's more galaxies than you would expect, and they are bigger than you would expect. Standard theories of galaxy formation say galaxies should form, blah, blah, blah. Here are all the various processes. People have studied those over the last 20 years. They know how quickly they should take to form. And what they find is that there's more galaxies that are well formed than expected. This is completely unexpected, and nobody knows the reason. But one reason could be that they were formed from these primordial cosmic strings. We had a seminar here a couple of months ago by Robert Brandenberger, my friend from McGill, talking about exactly that, showing that scenarios for cosmic string formation could account for the data from the Webb telescope. So this is now very much an open topic and reignited by better observational data. Okay, so cosmology and superfluids are super cool, and topological defects are super cool. So now we're going to talk about something else that doesn't get as much of the limelight, but is also really amazing. So what I want to tell you is about quasiparticles. I just want to make sure. Okay, so I want to tell you what the basic idea is. So the basic idea is this. What we're considering is a strongly interacting Bose fluid. Okay, I'm not talking about a Bose gas for now. I'm not talking about an atomic condensate or coal atoms. I'm talking about a strongly interacting Bose fluid. So it's dense, they're helium atoms, they're banging into each other, yet they're still at low temperatures in a quantum coherent, macroscopically occupied ground state. Okay, So the question is, can something simple emerge from this? And so the question we're going to ask is, what is the nature of the excitations of the system? So we're looking at the excitations above the ground state. That's the question. Now, what Landau had the idea that something very strange happens. He said that I can have sound waves in such a system, and as long as the sound waves are dilute enough, the sound waves will just behave like regular waves and they'll be linear. Okay? Now, in the second quantization worksheet that I gave you, how many of you did the last problem? Okay, so in that last problem, you've got a bunch of spores and springs, and you solved that problem quantum mechanically. Okay, and what did you end up proving in that problem at the end? So Chang, you did the problem, right?
This is with the atom chain.
It should have been a life-changing experience for you. Clearly it wasn't.
No, you helped me with this problem.
Yeah, that's what
How do you forget about it? It's insane. Okay, somebody else.
You take the Fourier transform, you see that even though the original Hamiltonian is strongly interacting, you can write it in a way that it looks like you have a bunch of non-interacting particles, non-interacting excitations at different wave numbers.
Yep. So what happens is that even if there's strong interactions, these sound waves are excitations that behave like free particles. And you derived this in that exercise. So if it didn't resonate, please go back and look at it. And so I don't want you to look at the math because I know you know the math. Okay, look at what it means. Okay, it's the exact opposite of what emergence is. Well, it's the same with emergence. Remember, in my picture of emergence was something becomes a solid, and then emergence is the springs that hold things together, and that was the springs are emergent. Okay, now we're going to take away the springs. We're going to see, so there's going to be two levels of emergence. One is atoms solidify into a crystal. In that example, it was a one-dimensional crystal. Now I've got springs that came from the fact that they broke translational invariance, and now you've got forces between the atoms, and they sit around lattice sites and oscillate. Now the next level is, now I look at those excitations. Those excitations, as you proved in the homework, if you don't know how to do it, ask me and I'll show you. Those excitations then behave like non-interacting particles. So I start off with interacting particles. They condense and form an interacting material, a solid, with springs, which are the elastic forces. You've derived elasticity, just like we did in the class, generalized elasticity. Now what you've discovered is that elasticity itself can be described by a new set of particles that behave as if they're ideal. So I've gone from interacting particles to a collective state with new laws of physics, new forces, to now being able to describe that by non-interacting particles that then move around. Okay, and there's even more to it than that, because those particles, you can say, I've now got a gas of these non-interacting particles. Okay, guess what? I can send a sound wave through this gas of non-interacting particles. Okay, not a sound wave through the real particles, a sound wave through these special created particles that came from two levels of emergence. Okay, and that sound wave is called second sound. Okay, and that's the thing that you can see in the video. Okay, so let me just finish this. We're slightly over time, and then I'm just going to write down one formula, and then we'll talk about this next time. So the idea is that the energy of the system is now going to be E naught, and then if I've got a bunch of non-interacting particles, so I have the number of those particles times the energy that they have, that will be the energy of those particles. But there's one particle, or one type of particle for every momentum. So N of P tells me the number of particles with momentum P. Epsilon of P tells me the energy of a particle with momentum P. And then what I have to do is I have to sum over momentum. And so this is a description of the system. And then there's higher order terms. This thing here is the many-body ground state of the system. This thing here is the number of quasi-particles with momentum P. And this is the energy spectrum of the quasi-particles. And because I've written the form like this, dot, dot, dots, we're not going to talk about, this says that these are non-interacting. Okay, by the way I've written this down, this is, by definition, non-interacting quasi-particles. Okay, now, this is magic. I've got a strongly interacting many-body system. I can't calculate anything worth a damn about it. So what Landau's brilliant idea was, is I can't calculate that. Okay, but I can calculate small excitations above that state. So you look at the difference between the actual energy and this, and it is of this form. So this you can calculate. And that's what we're going to do next. Now, what we're going to do is you might say, well, I don't believe this is just Landau, and okay, well, Landau's a genius, so we should believe it, but how do I really know it's true? Okay, so we're going to do an example. We're going to take a Bose gas, and then we're going to switch on interactions between them, and we're going to make those interactions small. Even though they're small, they are horrifically difficult to handle mathematically, okay? But we can do the calculation. There is a way to do it that you guys can learn at this level, and I'll teach it to you. And you can derive this, and you can derive this explicitly, and it just drops out, and it's amazing, okay? So you can see that this is really true. This tells you that if you want to look at very complicated, strongly coupled systems, there is a way, there is a question you can ask where you can actually do a calculation and learn something important. Furthermore, you can actually explain experiments. So next time, where we're going to start is we're going to talk about how Landau knew this idea was correct. Okay, and it's amazing how he knew that it was correct. It's fantastic. And it comes down to thermodynamics. And then we're going to see how you do the calculation. Landau didn't figure that out. His arch enemy, Bogoliubov, figured this out. Okay, Landau thought he was the smartest person in the world, but he kept on being out-calculated by people who he thought weren't as smart as him. And one of them was Bogoliubov, another was John Bardi. And so we'll see next time how you can calculate this using a brilliant trick, a method that was invented by Bogoliubov, which it turns out to be related to a normalization group and all sorts of other things. Okay? And if you want to learn more about it, I have an essay I wrote about this, which is about to be published in a book on 50 years of the normalization group. And it's actually on Teams. I will repost it, or maybe you can repost it if you remember. So you can read that if you're interested, just for sort of cultural background. Okay, we've run out of time and there's a class in here next, so we should leave. Okay. All right.
If you included interactions between the quasi particles at this hierarchy.
So wait.